Have you ever stopped to really think about what happens when you type go run or /app and just hit enter? On the surface, it seems so simple. We've got this file on our disk, just a bunch of static bytes, and then poof, in an instant, it's a living, breathing process running in memory. We kind of treat this like magic, but come on, as developers, we know there's no such thing. It's actually a super precise, fascinating sequence of events, all orchestrated by the Go compiler, the linker, and your operating system. In this explainer, we're going to deconstruct that entire journey. We'll trace the path from the moment the OS loader touches your file to the very first instruction of your main function actually running. By the end of this, I promise you'll have a deep and accurate mental model of how a Go program truly comes to life.
So here's the game plan for how we'll unravel this whole process. We're going to start by solving a little technical mystery. What is the real entry point of a Go program? And trust me, the answer is fundamental to how Go is designed. Then we'll dissect the executable file itself, thinking of it like a complete machine just waiting for power. From there, we'll watch as the operating system gives it that initial spark of life. Now, this leads to the most crucial part, the Go runtime bootstrap, where the program literally builds its own execution engine from scratch. Only then will we get to see your code's first breath as the main Go routine is finally born. And to wrap it all up, we'll tie all these pieces together into one single mental model you can use to reason about your own Go applications. All right, let's dive. Okay, so let's kick things off with a puzzle. It's a question that gets right to the very heart of how Go is designed. And, figuring out the answer is the first big step in building our mental model. It might even surprise you a little bit. So here's the question. When the operating system loads your binary into memory and decides, okay, time to run, what is the very first line of your application's logic that gets executed? Just think about it for a sec. The most common answer, the one that seems totally logical, is the main function in your main package. I mean, it's called main for a reason, right? That's the entry point we all write. But is that actually what the CPU sees first?
Nope, not even close. In fact, main.main is one of the last things to run in the entire startup sequence. Before your code can even think about printing Hello World, a whole world has to be built first. See, your code makes a ton of assumptions. It assumes it can create goroutines, it assumes it can allocate memory on the heap, and it assumes a garbage collector is watching its back. None of that stuff exists when the process first starts. Believing main.main is the start is a really common misunderstanding, and correcting it is the key to truly getting Go's execution model.
The real entry point is actually a special low-level function deep inside the Go runtime itself. On a 64-bit Linux system, you'll see it named something like _RT0_AMD64 Linux. Let's break that down. _RT0 stands for runtime 0. It's the absolute ground floor. The rest of the name just specifies the architecture and the OS. So during compilation, the Go linker literally hardcodes the memory address of this function right into the executable's header. This is the address the OS is told to jump to. So why is this so necessary? Well, because your Go code is high level. It makes these powerful assumptions. When you type the Go keyword to start a Go routine, you're assuming a complex scheduler exists to manage it. When you call make to create a slice, you assume a sophisticated memory allocator is ready to hand you some memory. At the very start, none of that exists. The runtime has to run first to build that whole environment. The scheduler, the allocator, the garbage collector, everything your code needs to survive. So to understand how the runtime builds this world, we first have to look at the blueprint it's working from. Let's just rewind for a moment, back to before you even run the program, and let's just look at the executable file itself. The best way to think of it isn't just as a file, but as a complete machine, fully assembled with all its parts in place, just, waiting for someone to turn on the power. Inside this one single file, the Go linker has packed 3 distinct worlds, all frozen in time. First, of course, there's your code. Every function you wrote, every variable you declared, it's all been compiled down into raw machine instructions, and it's just sitting there, crystallized into bytes. Second, and this is a huge design choice in Go, the entire Go runtime is baked right in. The scheduler, the garbage collector, how channels work, the memory allocator, it's not being pulled from your system when you run it. It's already part of your executable. This is exactly why Go binaries are so portable and self-contained, and it's also why they're often a bit bigger than a similar C program. And third, there's this critical metadata. Think of this as the instruction manual for the runtime itself. It has things like module data, which is basically a map of the whole program, all the types, functions, and packages. It also has something called PCLN tab, or the Program Counter Line Table. This amazing little structure is what maps raw machine code addresses back to your source code files and line numbers, which is how Go can give you those beautiful, readable stack traces when a panic happens. So these three worlds are all neatly organized into standard, well-defined sections inside the executable file, in a format the OS totally understands. The .text section, that's where all the machine instructions live, both your code and the runtime's code. And critically, it's marked as read-only and executable. This is a super important security feature called WXOR-X, or write X or execute, which basically prevents an attacker from overwriting your running code with their own malicious stuff. Then you've got .row data, which holds other read-only things, like string constants. .data is for your global variables that you've already given a value, like var myglobal equals 42. And then there's the really clever .bss section. Imagine you declared a huge empty global slice, like var big buffer 1000 int. Instead of storing 1,000 zeros in the executable file and making it way bigger, the linker just makes a note in the .bss header saying, hey, we're going to need space for 1,000 integers. The OS is then responsible for allocating and zeroing out that memory when the program loads. It's a simple but really effective optimization. All right, so our machine is built and it's just sitting there dormant on the disk. Now, you go to your terminal, you type ./app, and you hit enter. That command is a request, a call to action for the operating system. And now the OS begins this purely mechanical, totally predictable process to give our static file the spark of life. The OS loader, which is a part of the operating system that knows absolutely nothing specific about Go, springs into action. First, it reads the executable's header. This header follows a standard format, like lfun Linux or Mago on macOS. And it tells the loader the whole layout of the file, where every section is, its size, and what permissions it needs. Second, it does something called memory mapping. It creates a brand new virtual address space for our process and starts mapping the sections from the file into it. The .sec section from the file gets mapped into a memory region marked read-only and executable. The .data section gets mapped into a read-write region. Third, it handles that .bss section. It allocates a fresh block of memory for all those uninitialized global variables and just fills it with zeros, making good on the promise the linker made. And finally, the OS performs its last and most important job. It reads the entry point address from the header, the address of our srt0 function, loads that address into the CPU's instruction pointer register, and then it just jumps to it. At that exact moment, control is handed over from the OS to our program. As far as the OS is concerned, its job is done. The program is now running. But let's just pause right here and be super clear about the state of our program at this exact instant. The raw materials are there, sure. The machine code for your program and for the runtime are sitting in memory pretty much just as they were in the file. But that's it. Think of it like this. The OS has delivered all the unassembled machinery to an empty factory floor and turned on the main power breaker, but none of the machines are configured or connected to each other. There is no heap for dynamic memory allocation. There are no stacks for goroutines. There is no scheduler with its G's, M's, and P's. The entire dynamic world of a Go program is completely, totally absent. The OS just loaded the blueprint and flipped the switch. Everything that actually makes Go feel like Go must now be built from scratch by the program itself. And this is where the real magic happens. We have just jumped to that art0 assembly function. This tiny, carefully crafted piece of code is the seed from which the entire Go runtime environment is going to grow. It's the very definition of bootstrapping, the process of a system literally pulling itself up by its own bootstraps. And this presents a really fascinating technical puzzle, right? A kind of chicken and egg problem, the bootstrap paradox. The Go runtime initialization code is itself written in Go. But Go code needs the runtime services to even function. It needs a memory allocator to create new objects. It needs a scheduler to run on. So how on earth can Go code execute to build the very environment it needs in order to execute? It's a classic dilemma. So Go solves this paradox with two special foundational structures that are created before the main scheduler even exists: G0 and M0. The runtime carves out a special Go routine called G0. Now, this is not like a normal Go routine you create. It doesn't run on a small, dynamically growable stack that would need an allocator. Instead, G0 runs directly on the main, large system thread stack that was given to us by the operating system. This gives the initialization code plenty of room to work without needing a memory allocator just yet. At the same time, it creates M0. The M here stands for machine, or an OS thread. So M0 is the runtime's internal data structure that represents that single OS thread we currently have. These two structures, G0 and M0, are created very, very carefully using low-level assembly code, providing the bare minimum execution context needed for the rest of the Go-based initialization functions to start running safely.
All right, now that we have this minimal foundation, the Bootstrap can get going through a very clear chain of command. The initial art0 assembly code handles the most primitive setup, like getting arguments from the command line, and then it calls art0 go. This function is basically the bridge from the assembly world into the Go world. From there, we call OS init. This is where the runtime starts asking the operating system questions to learn about its environment, like, hey, how many CPU cores are available, or what's the memory page size? This info is vital for configuring the scheduler and the memory manager. And all of this leads up to the main event, the master initialization function, runtime.setInit. Now, what's really amazing is the sheer scope of scheduinit. This one function is where our dormant machine truly comes alive and becomes a proper Go runtime. It's just a whirlwind of activity. First, it initializes the memory allocator. It sets up the main heap area and all the complex caching structures like mcache and mcentral that make and new so incredibly fast. Second, it initializes the garbage collector, using that pseal and tab metadata the linker gave us to get all the data structures ready to track pointers and clean up memory later. Third, and this is critical, it initializes the scheduler. It checks the GoMax PRAS environment variable, which tells it how many OS threads can run Go code at the same time, and then it creates a P, which is an abstraction of a processor, for each available core. Each P gets its own local queue for runnable goroutines, preparing the program for true parallelism right from the very start. And finally, it initializes all the other subsystems, the network polar for handling I/O, the timer heap for things like time.sleep, and the mechanisms for panic and defer. By the time scheduinit is done, the entire Go execution engine has been built in memory, and it's ready for work. So the stage is now fully set. We have a heap, we have a garbage collector, and we have a fully functional scheduler, with idle processors just sitting there waiting for work. The entire Go runtime is alive and kicking. But our own code, our main.main function, still hasn't run. There is one final, crucial step before that can happen. The runtime now performs its final act of creation. It calls a function called new proc to create a brand new standard Go routine. But this one is special. It's configured to execute our main function. A small standard 2 kilobyte stack is allocated for it from that newly created heap. This new Go routine is then marked as runnable and is placed into the local run queue of one of the available Ps. Now, finally, the scheduler has work to do. The initial thread, M0, which has been driving this whole Bootstrap process on the G0 stack, now just transitions into its regular job as a worker thread. It finds the new main Go routine in the queue, it performs a context switch from that big G0 stack to the new Go routine's small stack, and it jumps to the first instruction of main.main. And at that precise moment, your code takes its very first breath. And this just brilliantly illustrates the difference between that setup phase and normal execution. The Bootstrap Go routine, G0, was a special case. It was like a temporary construction worker running on a huge, fixed stack that the OS gave it, and it existed before the scheduler was even alive. In contrast, the main Go routine that runs your code is a totally standard citizen of the Go world. It runs on a small, managed, growable stack, and its entire life is controlled by the GMP scheduler that G0 worked so hard to build. And on that note, subscribe to our Gokun channel for deep dives into Golang internals, architecture, and execution flow, advanced concepts rarely covered on YouTube, available for free, and rest assured we will explore the stack, heap, and GMP scheduler in greater detail in separate, dedicated videos. Please subscribe to ensure you do not miss those upcoming lessons. So, we've done it. We've completed the full journey from a static file on disk all the way to your running code. Now, let's just consolidate everything we've learned into a single, powerful mental model that you can use to reason about any Go program you write. Before we summarize the whole model, let's touch on the single most important practical takeaway from this entire process. We've established that the main Go routine is the first user Go routine, but it's also special in how it ends. When your main.main function returns, the program is considered done, period. It triggers a system exit immediately. The runtime does not wait for any other Go routines you might have started to finish what they're doing. They are instantly and unceremoniously terminated. This is such a classic source of bugs. If you start a Go routine to do some background processing and your main function finishes right away, that background work will never happen. That is why you must use coordination mechanisms like a sync.wait group to explicitly make the main Go routine wait for others to complete.
So our complete mental model can really be seen as these three distinct worlds, or layers, all working together. First is the static world, created by the linker. This is the blueprint, your executable file, containing the compiled code, the runtime, and all that metadata. Second is the dynamic world, built by the runtime at startup. This is the living system, the heap, the goroutine stacks, and the scheduler's GM and P state, all of it conjured into existence in RAM. And third, you have the foundation, which is provided by the operating system. This is the raw material, the memory pages, the OS threads that the scheduler's M's are built on top of, and the system calls for I/O that make things like networking and file access possible. The Go runtime uses this foundation to build its powerful high-level abstractions for us. And with this three-world model, you now have clear first principles answers to some really fundamental questions about Go. Why are Go binaries relatively large and self-contained? Well, because they contain the entire blueprint for the dynamic world. The whole Go runtime is packed right inside. Why can't your other Go routines outlive the main function without you explicitly coordinating them? Because the lifetime of the main function defines the lifetime of the entire process. When it returns, the OS is signaled to exit, and the entire dynamic world is just torn down. Understanding this complete journey, from those dead bytes on disk to living code in memory, it transforms Go from a tool you just use into a system you truly, deeply comprehend. And that right there is the foundation for writing more efficient, more correct, and more robust software.